Hello, everybody. Welcome to another exciting edition of HL Chemistry Flipped Classroom. This is Mr. Los. We're going to talk about reaction order today, and let's get cracking. Reaction orders. This goes along with a note sheet that I linked in the distance learning packet. And, it's not absolutely necessary that you have that note sheet or print out a physical copy of it, but it is going to be helpful because there's like some data tables and stuff in here that might be kind of a hassle to write it all down. Do whatever works best for you. Okay, so let's start off by talking about what a reaction order is. So we've talked in the previous section about the fact that concentration of a reactant affects the rate of reaction, but exactly how and what is the proportion? Is it a direct relationship? Is it some kind of exponential thing? So a reaction order is a way of describing, in particular, in the case of a certain reaction, how changes in concentration will affect the reaction rate. Initial rate is a term you'll see brought up in this a lot. It just means the rate at the very beginning of a reaction. Typically, that's when we measure these rates. So it's just something you'll see, and I just want to bring it up to you. So what we're going to be working on today, a big focus is writing these things called rate expressions or rate laws. And you see kind of the generic form of it there. So the rate of reaction equals K, which is going to be some constant. A and B are the orders. And what the orders are going to be is exponents that go along with the concentration of A. So 1, if you put a coefficient of 1 there, that would be considered to be first order. Now, since 1 doesn't actually change the value, generally the 1s aren't put there. But 2 would be a second order reaction. 3, although that's not very common, would be a third order reactant, and so on. It is possible for there to be 0 order. And a couple of the things to keep in mind about here is K is constant. It's constant for a particular temperature. The only thing that affects K is temperature. Higher temperatures increase the value of K. And if we just think about that mathematically for a second, assuming we're holding concentration of A and B constant, we do know that the rate is higher at a higher temperature. So what's changing, or the K is different, and the K is higher at the higher temperature, because if K is larger, the rate becomes faster. So reactions are faster at higher temperatures. And then brackets, I don't know to what degree we've encountered this before, but when you see something in brackets, it means a concentration in mole per cubic decimeter or a molarity. So I think you'll see what I'm talking about a little better when we look at some examples here shortly. How we speak about this, and by the way, you're going to see me, when we do real rate expressions for real chemical reactions, we are always going to put the actual reactants in there. I'm going to do some generic ones with X and Y and so forth, but please, 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 when you do real chemical reactions, put the actual reactants in there like they are here. So here's a rate expression for some reaction involving hydrogen and iodine. And how we would speak about this, if we would say that it is first order with respect to iodine, because there's a invisible 1 coefficient there, which you don't need to put, because mathematically it doesn't affect anything. So you would say it's first order with respect to iodine, it is second order with respect to hydrogen, and the reaction is third order overall. And I'm simply getting that third by doing 2 plus 1. If they were both 2, it would be considered to be a fourth order reaction. If they were both 1, it would consider to be a first order. So I'm simply summing the orders of the individual reactants to get the overall reaction order. There's a thing that we're going to talk about called the method of additional rates, and it's a way of figuring out experimentally reaction orders. Reaction orders can only be figured out by experiment or by being presented with some kind of data. You cannot look at a chemical equation, an overall chemical equation, and tell what the rate law is going to be. So there's a variety of ways of determining reaction orders, but they involve typically running the reaction, having some way of measuring the rate. We talked a little bit about that can be difficult depending on what you're doing. But you vary the concentration of different reactants, and then you can get a feel for how concentration is affecting rate. And we're going to look at some data, and I think you'll see a little better what I'm talking about here. So, a lot of information on this slide here, and what this slide is doing is telling you kind of a very formulaic approach of figuring out reaction orders. I would never actually use this formula. I would just look at the data and kind of think about it in almost all cases. And again, this is going to be more clear when we see some examples, but what we're going to do is find a pair of trials where the concentration of one reactant is changing and the other is being held constant. And the reason for that is, the reason why we want to hold, it's like any kind of controlled experiment, right? We want to hold everything constant but the one thing we're interested in. So we're trying to find out how concentration of a certain reactant affects the rate, we want to make sure everything else is staying the same, including the concentration of the other reactant. And we're going to pick 2 trials. You'd have to do at least, depending on the situation, probably a minimum of 3 trials to do this. You're going to pick trials where the concentration is changing. Concentration 1 should be larger than concentration 2, and then you're going to compare the rate in those 2 trials. And the exponent, and that is an exponent, it's not times x, that is to the x power. The exponent there is going to be the reactioner in that case. And again, there's ways around using this equation, but I'm just going to present this to you as an option. It's not going to be given to you or anything, so you'd have to memorize it if you were going to utilize it. So let's go ahead and actually look at one of these. So this is kind of what I'm talking about, like this data table. I think it would be nice if you have the printed version, or at least if you have the digital version to reference and handwrite some of this stuff rather than trying to write down this whole data table. So looking at this experiment, which is just a generic experiment to make my life easier and making up the problem, we've ran 3 trials and we've varied the concentration of x and y each time, and we've measured the rate. Apparently we're measuring the rate of formation of xy in mole per cubic decimeter per second. So change in concentration over change in time, typical rate unit. We're going to find all 4 of those things, and then we're actually going to find one other thing. So I'm going to switch over to the notebook sheet here. I'm also going to hide my little face here, or I think I'm going to. Let's put them up here. Well, okay. I guess maybe you'll be looking at... Maybe it is hidden already. I guess maybe you can't see it. Okay, whatever. Or else you're going to be looking at the ceiling. I think it is hidden already. Okay, so I'm gonna work through this here. Hopefully, sorry if that made loud noises. Okay, find the order for each reactant. So I'm going to do this one at a time. Well, let me just say this first. We know already, before we even do anything at all, that this is going to look something like this. Like, I can write this much of it before we do anything. And the only thing that is going to matter here, or the only thing all of what I'm about to do is going to help us figure out, is if I should put any exponents up there. So let's try to figure out the order with respect to x first. Now I want to do a pair of trials. Ideally what I'm looking for here is a pair of trials where x's concentration is changing, but y's concentration is staying the same. And the reason why I want to do that is so that I can isolate the effect of just x. I wouldn't want to pick trials where both of them are changing, or that's going to confuse the issue. So let's pick trials 2 and 3. So remember, we're going to do concentration 1 over concentration 2 to the x power equals rate 1 over rate 2. And then we're going to basically solve for that x. And again, I'll explain like maybe an easier way to think about this in a moment. But so let's let the higher concentration be concentration 1. That's going to be 0.4. So I'm getting that from right here. And then the lesser concentration would be concentration 2 to the x power. And then I'll make sure I put the rate that goes along with the 0.4 trial, which is 1.2 times 10 to the minus 2. And then 3.0 times 10 to the minus 3. Now, if we do the math here, that is 2 to the x equals 4 when I divide those two out. And, just thinking about it, rather than doing any log rules or whatever to solve this, 2 to the x power equals 4. Well, that would be to the second power. So x is 2, and that means x is second order, and that means when I do my rate expression, I should put a 2 in there like that. So basically what happens is by whatever factor I change the concentration of x, that gets squared, and that's what happens to the rate. So in other words, I double x, I quadruple the rate. Okay, so let's find y. So y, I want to pick a different pair of trials. I want to pick trials where y is changing, but x is staying the same. 1 and 2 are looking good for that. And the concentrations again are 0.4 and 0.2 to the x power. And then this time, the two rates are 3 times 10 to the minus 3 all over 1.5 times 10 to the minus 3. So 2 to the x equals 2. That means x is 1. 2 to the first power equals 2. And whoops, and that means that x is first. Y is first order. I solved for x in this equation. Y is first order. So yeah, I mean, you could put a little 1 there, but mathematically that doesn't change anything. So yeah, actually we've done A and B. We've found the order for each reactant. X is second, Y is first. The overall order of this reaction would be third. These, by the way, sometimes people think that these orders have to be different. They don't. They could both be 2, although they'd be unusual. They could both be 1 or whatever. Okay, value of K and unit. Now, let's leave the unit thing aside for just a second. Let's just see if we can get the numerical value for K here. So now I have an algebraic expression, right? And as long as I know everything but one thing in it, I can solve for that thing that's missing. That's how algebra works, right? So I can pick any one of these 3 trials. Let's pick trial 1 just for the heck of it. And what I'm going to do, so here's my algebraic expression that I wrote. I'm going to solve this bad boy here for K using information from my experiment. So to solve for K, I could move both of these things over here, divide both sides by x squared y. So rate divided by the concentration of x squared times concentration of y is going to equal K. So again, plugging in stuff just from the first experiment, 1.50 times 10 to the minus 3, that's 10. My x is 0.2 squared, and my y is 0.2, and all that is going to equal K. So if I do that calculation, just need to crunch through the numbers there and not have this keyboard pop up. I do believe K is about 0.1875, maybe 2 sig figs here, so 0.19. And we're gonna talk about the unit here in just a moment. But let's skip ahead. Overall reaction order, I already mentioned it's third, 2 plus 1. Okay, so here, now that we know K, I can find the rate at any concentration of x and y. Again, I got an algebraic equation now. As long as I know everything but 1, I can find that thing that I'm missing. So now that I know K, I can find the rate, call this 0.19, when x is 0.3, don't forget to square it, and y is 0.25. So I just really need to multiply all 3 of those things together. And I'm going to get, I believe, 0.00, call it 43 for 2 significant figures. Now here we can determine the unit. It's going to be the same as the rate given here, which is mole per cubic decimeter per second. Oh, by the way, yeah, this last question wasn't on the first slide that I showed you, but I do think it is on your note sheet. So yeah, that question right there. So that's the rate, and the rate can be the same as the rate unit given in the data table. All right, so going back to for a lot of people, the trickiest part of this is actually figuring out the unit of K. What's kind of unfortunate is that it does not have constant units. The units of K are going to depend and change depending on the exact situation. So I'll walk you through the whole business of figuring out the unit for K. There's also kind of a shortcut formula for figuring out K, and which I'll get to in a second. But one way to figure out the units for K is just do the crunching of numbers of basically what all of this business right here, so we already did the algebra, right? What all this business right here would actually like simplify to in terms of thinking of the units. So I'm going to repaste this down here just so we could see a little bit. Okay, so the units for K should be whatever is left after stuff is canceled and whatnot from all of this. So the rate, I'm going to write the rate in the kind of fractional form. May or may not be easier to look at it that way, but that's the unit for rate, mole per cubic decimeter per second. And then we took x and we squared it and we multiply it times y. Well, what are the units? What do these brackets mean? These brackets mean mole per cubic decimeter. That's the unit for both of them. But in the case of x, I squared that. And then I need to multiply that by another mole per cubic decimeter. Okay, so this top here, mole squared times another mole, that's mole to the third. decimeters cubed to the second power. When you take an exponent to another exponent, you have to multiply them, so that's 6. And then plus another 3, so that's dm to the 9th. When you multiply exponents, you add them. Okay, so now I got all of this business right here that I need to simplify. One way to think about that is dividing is the same as multiplying by the reciprocal. So multiply this by dm to the 9th over mole cubed. So all I'm doing is taking this and I'm flipping it, because dividing is the same as multiplying by the reciprocal, like I said. And that's just a way of helping me see what simplifies here. So that cancels and leaves 6 of those left over. One of these moles can cancel and leave 2 of those left over, and the second is going to be just left alone. So dm to the 6 mole squared second. That's the unit for K. Unfortunately, that's not always the unit for K. But we'll look at a bit of a shortcut for that in a moment. So I want to jump back to this guy here. Okay, so we did all of this. So like I kind of told you guys, I really wouldn't ever go through that business of finding the reaction order by an equation. What I would do is I would sort of think about it, and if the exponent is 0, that means something is going to be 0 order, which is possible. But what that means, kind of in a sense of just a conceptual sense, is if something is 0 order, that means the rate is not affected by the concentration of that particular thing. It is possible, it does come up every once in a while. If something is first order, that means there's going to be a completely linear relationship between the change in concentration and the rate. So in other words, if we double the concentration, the rate's going to double. If we triple the concentration, the rate's going to triple. If we quadruple the concentration, the rate's going to quadruple, and so on. Second order would mean there's an exponential relationship. So if you double the concentration, the rate would quadruple. If you tripled the concentration, the rate would go up by a factor of, wait for it, 9. If you quadrupled it, I'll let you think about what would happen there. So anyway, that's probably what I would do, is I would just examine the data and I wouldn't use that concentration over concentration 2 formula. Third order is maybe possible, but really it doesn't ever come up very often in reality. So here's another example here. And let's just see if we can figure out the reaction orders of these things without actually using that formula. If you want to use the formula, do it. Go for it. But let's just see if we can figure out without looking at that. So here we have 3 trials here. Concentration of C, concentration of D, we got them changing, we got the initial rate. Okay, so to figure out the concentration of, or rather the order of C, I want to do 2 trials where C is changing but D is staying the same. So 1 and 3 look like a good pair of trials. And what I might notice is that C is doubling, and I might notice that the rate is also doubling. You can always double check this with a calculator if you're not sure, but that's the case. So that means it's first order, because they're a linear, total linear relationship there. Now to figure out the rate of D, or rather the reaction order of D, I would use trial 1 and 2. C is staying constant, D is changing. And I might notice that D is changing, but the rate is not changing. So what that tells me is that D is actually 0 order. So what this looks like in terms of a rate expression is rate equals K times the concentration of C, which we found to be first order. Now D, we said was 0 order. Anything to the 0 power is 1, so typically we just leave it completely out of the rate expression, and we call the rate expression that. Okay, so the value of K, which we need to find, we can pick any one of the 3 experiments. And by the way, a good way to check to see if your rate expression is actually correct is try to find K from a couple of different experiments. And if you're getting different values for K, then, I don't know why I erased that, 0.005. If you're getting different values for K, something's wrong. So we're going to ignore D completely. I'm picking the information from trial 1 here. I'm plugging in the rate. I'm plugging in the C's concentration. Solve this by dividing both sides by 0.1. By the way, like this type of math is totally something they would expect to be able to do on paper 1 without a calculator. Dividing by 0.1 is the same as multiplying by 10, so that would be 0.05 is the unit for K. As far as the units go, so you know what, let's just go ahead and look at kind of our shortcut method here rather than me running through all that again. Our time is getting short here. So here is kind of the shortcut method. So it changes depending on reaction order. So here's a couple of equations you can use. You would have to memorize this if you're going to use these equations. So basically your options are memorize these formulas or learn how to cancel those units. Those are your two choices. Actually, you have a third choice, which is to get the units for K incorrect. So those are your three options. Memorize the formula, learn how to cancel them, or get the units for K wrong. Okay. So N in this thing is the overall reaction order. And so we're going to have a volume unit, whatever the volume unit is, like given in the data table. Moles is always going to be down here. And what is the time unit? It's most often seconds, but it might be minutes or something like that every once in a while. So for IB, typically we're given seconds for the time units, moles, and we're given cubic decimeters for the volume unit. So, like for example, for the one we just did, that's a first order reaction overall, right? Rate equals K times concentration of C. That's a first order reaction overall. So in this equation, N equals 1. So we're going to take our volume unit, which is cubic decimeters. Now, N is 1, right? So 1 minus 1 is 0. So that's going to be to the 0 power. Mole to the N minus 1. So again, 1 minus 1 is 0. And then our time unit is seconds. So actually, both these things to the 0 order are going to cancel out. And our unit here is going to be 1 over seconds, or seconds to the minus 1. So that's my unit for K in this one that I just did. The one we did previously, where that was rate equals K, and then we had X, which was to the second power, and 1. And show you how we could have found through the shortcut method the one we did previously to this. And so it would look like this. This was a third order overall reaction, so N in this case is 3. N being 3, 3 minus 1 is 2 in both of these equations here, right? That would be 3 minus 1 equals 2. So, for our unit for K, we have dm to the 3, but that gets taken to the second power, mole to the second power, and then our time unit was seconds on that. So, that's going to be dm to the 6th over mole squared seconds, which was the unit for K that we got after doing all that business with canceling the units that we did before. Okay, so one more thing that I want to look at is some graphical stuff. So this goes along with a page in your workbook. Okay, so the page that I'm looking at is this one. So we need to be able to predict and see what some of these graphs would look like. So we're told that this is a first order, so it's decomposition reaction and it's first order kinetics. And so the rate expression would look like this. Okay, so notice very carefully what units we're supposed to graph. Concentration of A versus time, concentration of AB versus time, and then reaction rate compared to concentration of AB. So let's think about this. A is a product, so its concentration is going to go up over time. Presumably, we're starting with 0 concentration, so it would go a little something like this. And it's not a straight line because rates slow over time. It's going to start fast and slow down. So it would look a little something like this. The slope of this line at any given moment is the rate. The AB graph would look similar, except AB being the reactant is going to decrease over time. And my graph might look a little bit like that. Now this is different. Basically what I'm doing in the third graph is I am graphing this function right here. That's my y-axis, right? That's my x-axis. This is the slope. This is just like y equals mx plus b, right? Same thing. Same graph. Don't need the plus b. It's a straight line. It's a straight line like that, starting at the origin. The rate's going to be 0 when the concentration of AB is 0. So it's just a straight line plot. Okay. Consider the 0 order reaction, like this. 0 order. Okay, so this is interesting. concentration of Wx over time. So here's the thing, being a zero order reaction would mean that the rate is not affected by the concentration. So I could do either one of these graphs first. Well, maybe we'll do this one first. What would the rate expression look like? Rate equals K times the concentration of that, but that's at the 0 power, so I wouldn't even put that in there. So rate just equals K. Rate equals some constant. So it would be like, maybe like that, right? Rate is just some constant value. It doesn't depend on concentration. Wx, of course, it would still decrease over time, but that's supposed to be a straight line. It's going to decrease in a linear fashion because the concentration is not affecting the rate. Normally, concentration does affect the rate. Remember, we talked about that's why reactions slow down over time. Here, it's not going to. So it's going to decrease at a steady state. This is an unusual situation, but it is possible in certain like catalyzed reactions and so forth. But that's what that would look like. Okay, so second order reaction. So the rate expression here is rate equals K times the concentration of CD, but squared. So graphically, this is like YMX squared, basically. Did I mention the slope is the value of K here in this type of graph? Yes, it is. Okay, so concentration of CD over time and reaction rate. Well, doing this one first, this is an exponential type thingy like that. And again, I'm basically just graphing this thing right here. As far as this one goes, similar, but it's going to be a more drastic type situation where changes in CD are going to cause a more drastic, so shape similar to this one, just kind of a more drastic effect as concentration changes, more of an exponential decay type thing. This one I'm going to leave for you. That's going to be a little bit of stuff that you can practice. This is a little more conceptual stuff, but thanks for watching. You know, as always, be in touch if you have any questions. Stay safe out there, and we'll hopefully see you soon. Bye.